Good morning. My name is Pamela Lara. I am a PhD candidate from the University of Texas at Paso. I am an NCAS-M fellow, cohort 3, and today I'm here to talk to you about the increase of the absorption coefficient due to black and brown carbon particle that we believe are due to the wildfires. So I'm very glad that I'm here, that previous presenters were talking also about wildfires. And so I have here some points. I'm not going to go to them, but I'm going to show you better. Let's see. I'm going to show you better what I'm talking about. So I'm going to start with the map of our city. So we are doing this study in a dual nationality. I am from El Paso, Texas. Our city is a border town with the Ciudad Juarez in Mexico. So this red line is the border between both towns to the north. You see that is El Paso, where the little heart is my university, UTEP, and to the south is Ciudad Juarez. And some important aspects of these two cities is that I mark here with this little red star, is the international bridges between both cities. Now, these international bridges see a lot of traffic during the day, not just private traffic, but also commercial trucks passing between those two cities. And because of the heaviness of the traffic, they spend a lot of time just hanging there, waiting to cross. Also, in this area of Ciudad Juarez, especially to the northwest side, there is sort of like a little bit a lower economic population. So a lot of people use this, for example, burning biomass, wood or charcoal, as even cooking or heating their houses. Also, there are a lot of brick factories. There are the other factories around, so there's a lot of things happening. And this thing between the two cities, these international bridges, these of the tracks standing there, creates a lot of pollution. And that is what it needs to be monitored. So one of the monitoring that is doing this is TCEQ, the Texas Commission of Environmental Quality, and our university. So we do several monitoring. We use, for example, one of our instruments is a bisal accelerometer. And but the instrument that I use is called a PAX, or photoacoustic extinctiometer. And very good. So let me tell you a little bit of what I am studying. So I am studying something that is called the absorption coefficient of this particle. Now, just to explain to you what is absorption coefficient. So we have a rate of light that interact with the particles, in this case, the black and brown carbon particles. And when the light interact with the particle, two things can happen. The light can bounce off of the particle. We call that the not absorption coefficient, but oh my gosh, the word just abandoned me. They bounce off. But the second part of the interaction is that part of that energy that comes from the light is absorbed into the particle. And that is the part that I am interested in. So black and brown carbon are aerosol particles. The source is similar between those two particles. They are mostly for the incomplete combustion that happened during, for example, biomass burning, but also for the combustion inside of diesel and petrol engines. And it's important to study them because first, they are pollutants. And in El Paso, Texas, all the studies that have been done about these particles are concentrated on black carbon. Nothing has been done on brown carbon, so we are the first one doing this study. And as black carbon, how they're a risk to the health of a school-age student. Also, as pollutants, in us, aerosol particles, they stay in the air between 10 and 14 days. But when they land in water, they land in snow, they land in water, and this unbalance the ecosystems of those regions. The part that I am interested in is in this light absorbing capability of this particle. And why? Because this light absorbing contributes to global warming through a step that is called radiative forcing or positive radiating forcing. And as I was explaining, we use these instruments, the PAX instruments, we use two of them, one at 70 nanometers. It has a laser that interacts with the incoming particles at that wavelength. And at that wavelength, that instrument is interacting mostly with black carbon particles. We use another one, a 405 nanometers instrument or PAX, but at that wavelength, it interacts, it's like a bag. We have here the interaction with black carbon particles, the interaction with brown carbon particles, and maybe negligible and interact with mineral dust. And also we use other platforms. For example, we use the TCEQ camps, but also we use HRRR smoke. That is a high, I have to write it down, high resolution rapid refresh and high speed. Thank you, Dr. Miles. I don't know if she's here, but we use these two NOAA models. And so let me tell you a little bit. So I was telling you that we have, because of this interaction between these two towns, we already have something that we call a baseline amount of absorption coefficient due to black and brown carbon. In this graph that you see here on the x-axis, we have the diurnal average for the whole season. And our season is what we call the wildfire season. For us, it's just August and September, so we have these 2 months of data. On this side of the y-axis, we have the absorption coefficient as measured for one of the instruments, that is the PAX at 870 nanometers. In black and in blue, we have the absorption coefficient as measured by the PAX of 405 nanometers. Mind you, they are at different scales because of this difference of energy. The interaction with the particle is different. But these are our sort of baseline. For the PAX 405 is around 5.9 megameters per megameters, and on the PAX 870 is around 0.9 per megameters. That is our baseline. Now we do have an hypothesis. And this hypothesis is that we have seen that during the summer, this baseline jumps up, increases. So our hypothesis is that this jumping happened because of the West Coast wildfire, that somehow because of this playing between the high and low pressures, the smoke arrived to our region. We were able to detect between the August and September 18 instances that we call event days when this happened. Most of the wildfires were in California, but we have some also happening in Oregon, lower here, Nevada, even Idaho, and all the way to Montana. So we call these event days. We have 18 of these event days. And here using HRRR, we have this map that I put together of the September, summer of September wildfires. So we see how the fire started on the West Coast and this goes north. Most of it goes to the East Coast, but because of the circular pattern, some of the smokes arrive to our region that we are here in this little corner of the state of Texas. So you can see there how this map show by coloring code and by micrograms per cubic meter of mass of pollutants, in this case PM 2.5, but the black and brown carbon are part of the PM 2.5. They also arrive in the red and darker colors. We see where is the source. So we don't get much from the source, but we do get part of the smoke. As a primary, maybe directly from the source, and sometimes as a secondary, we get it from the smoke that is located in other areas. So here I have also the high-speed model that I was telling you about, and here we have these specific dates. For example, it's just any day inside of our season, wildfire season. We have the high-speed model with 72 hours backward trajectories. And so the high-speed model measures the trajectories of air parcels. So we see that for these specific days, and this is the HRRR in that day, we see that the wind is bringing whatever it brings from this area, from sort of the center of Texas, but also to a higher altitude from all the way there from the north. So we are bringing In the lower altitude, we are bringing smoke from this region here that I call sort of a secondary part because we are not bringing directly from the source, but from this area. And now what I have here is sort of a comparative graph where I combine the baseline for the region with what happened with these event days. So again, it's a diurnal average. And in red, you see the jump between the baseline that are here all the way to this event. And we see a big jump, isn't it? For example, for the packs, it was around what? 5.9, and it jumps all the way to 11.4. And for the packs A70, it was from 0.9 all the way to almost 3 per megameter. So it's a huge jump that happened during the event days. Mind you, we're still inside of sort of like the EPA standards, but there still accumulates, and this is actually our average. So we have good days, and we have not a good days, and we have very bad days. I just want to, just a little bit about brown carbon. So the 405 nanometers instrument, this one is taking sort of a big bag of the absorption coefficient. Inside of that big bag, we have black carbon absorption coefficient, brown carbon absorption coefficient, and a little bit of mineral dust absorption coefficient. So how do we distinguish which one is which one? And we do that sort of through some mathematical extrapolation. And we do something that is called the Angstrom exponent. That is just, the Angstrom exponent is a measurement that gives us a relation, an inverse relationship between this exponent to the size of the particle. And we use a comparative analysis between what the A70 nanometers extensiometer gives us to the 405 nanometers. And then we extrapolate which portion of that goes to black carbon, which portion of that goes to brown carbon, and then this negligible mineral dust that actually we don't measure, but we absorb into the other measurements. So in this one here, then we have just the brown carbon. And why separated? Because in El Paso, they have never been on the study of brown carbon. So for that, it was important that we can put it out there. So in black, we see the baseline for brown carbon, and in red, we see this event days for brown carbon. It's not a huge jump, but it's still a jump, isn't it? And so in conclusions, we have determined through our study that indeed, the jump that we see in the summer happened because of the smokes from the West Coast. We also have determined that our instruments are able to measure this smoke, even though it is very diluted in the sense that we don't see, as I showed you the HRRR map, we don't see smoke coming directly from the source, but we still are able to see. So hence, the atmosphere of El Paso and Ciudad Juarez are affected by these wildfires happening in the region. And we see here the percentage, there are big percentages of a jump from this baseline. This is the future research from the PAX 405. We see that during a baseline, the brown carbon is mostly due to the smoldering of a wildfire, of a biomass burning. And you see that very clearly. If you have burned, I don't know, in your backyard, maybe the debris from your garden, you see that whitish brown smoke, that is brown carbon. And so it comes from smoldering. And we see that in summer. In winter, we know that happens. And my colleague here is going to do a poster presentation about that. In winter, we know that it's because people is burning biomass to heat the houses. But what is happening in summer? Why do we see such a huge amount of brown carbon happening in summer? And also, we want to repeat, well, we have tons of dust storms in El Paso, Texas. So how much of that 405 is truly negligible? And then we want to do a sort of like a error analysis of what is going on. That is my acknowledgement. Thank you very much, especially to NCASEP, my references, and thank you, and I'm ready for questions.
Thank you so much, Pamela. We have time for one question. Any questions?
Thank you.
Really great talk. again, wildfire person. So have you decided to run some forward trajectories from these wildfires out west? Because some of your back trajectory didn't necessarily indicate that it goes all the way up to the west coast. So
Yes.
have you ran some of those fires?
So in the beginning, we did forward trajectories. In the beginning, we did forward trajectories. But sometimes, as you say, since we are in this region on the map, that as you mentioned before, most of the smoke goes to the east. So there has to be some playing in the air pressure, high-low pressure for us to get there. So we decided that a better information would be with the backward trajectories. That answer your question?
Yeah, yeah.
Very good.